So section 5.1, orthogonality. Let's see, before we start with the first example, we already know what's the meaning of orthogonal. We're gonna say that these two vectors, if we have two vectors orthogonal, that means the dot product of these two vectors is going to be 0. Now, orthogonality, that means more than one vector. That means two vectors, three vectors. So we're gonna say orthogonal set. So if you look to the first question here, they're just telling you find the dot product of each pair of the given vectors. Dot product. So question 1, we have v1 equal, the first vector is 5, 1, -1, and v2 equal -1, 4, -1, 4, and 1, -1, 4, and 1, and v3 is going to be equal 4, -4, 16. 4, -4, and 16. The dot product between v1 and v2, be careful, it's a dot product. So it's going to be 5 times -1 plus -1 times 4 plus 1 times 1. And the result is going to be -5 minus 4 plus 1. And the result is going to be -8, because -9 plus 1 is going to be -8. So now v1 times v3. That's what they're saying. Yeah, the second one, v1 times v3. So here is v1, here is v3. So it's going to be 5 times 4 plus -1 times -4 plus 1 times 16. And it's going to be 20 plus 4 plus 16. So 20 plus 16 is going to be 36 plus 4 is going to be 40. Let's check the vectors. -4 and 1. Yeah, there is something wrong with the first vector. Why I put 5, 1, -1. -1. So that's mean 5 times -1, 1 times 4, and here is 1 times 4, and -1 times. So in this case, it's going to be -5 plus 4 minus 1. So -5 plus 4 is going to be -1, minus 1 is going to be -2. And with the second one is going to be with this vector, which is 4, -4, 16. So it's going to be 5 times 4, 1 times -4, and 1 times 16. So it's going to be 20 minus 4, which is 16, plus 16 is going to be 32. This one is -1 times 16. That means it's going to be minus 16, and it's going to be 0. V1, now V2 times V3. We're just doing the dot product. V2 times V3. So it's going to be -1 times 4 plus 4 times -4 plus 1 times 16. and it's going to be -4 minus 16 plus 16, and the result is going to be -4. So this is just the dot product, and they ask you determine if the given vectors. Let's check that first. This is -2, and the second one is 0, and the third one is -4. They ask you here, determine if the given vectors form an orthogonal set. The orthogonal set, it's a set, not two vectors. We can't say orthogonal vectors. Orthogonal set, because this is a set of v1, v2, and v3. That means the dot product of each two vectors is supposed to be equal 0. The dot product of v1 and v2 is -2. The dot product of v2 and v3 is -4. That means this is not an orthogonal set. So the first concept, the orthogonal set, if the dot product of every two vectors is supposed to be equal 0. So that's you're gonna check. If they're telling you find or prove that this is orthogonal set, that means you have to do the dot product between two vectors, and the result is supposed to be equal 0. But we're gonna do the same thing with the next example, but now we have 3 vectors, and each vector with the 3 components. So we're gonna multiply v1 times v2, and v2 times v3, and v1 times v3. So the second one, we have v1 equal 6, 9, -3, 6, 9, -3, and 12. And v2 equal -6, 3, -6, 3, -3, 0. And v3 equal -4, -6, 2, 7. That's mean v1 times v2, the dot product between v1 and v2. So (6) times -6 plus 9 times 3 plus -3 times -3 and plus 12 times 0. So it's going to be -36 plus 27 plus 9 plus 0. And this one is going to be so -9 plus 9, because -36 plus 27 is -9 plus 9 is going to be 0. That's mean the dot product between the first two vectors equals 0. Now we have to check v1 times v3. If you check here on this example, they're telling you to find the dot product between these vectors. But what about if on the test, you have to do the multiplication, the dot product between v1 and v2, v1 and v3, and v2, v3. So now v1 with v3 is going to be 6 times -4 plus 9 times -6 plus -3 times 2 plus 12 times 7. And this one is going to be -24 and minus 54. And here is -6 and 12 times 7. 12 times 7 is going to be 84 plus 84. If you add these together, this is -60 and -80, -84 plus 84. So the result is going to be 0. Now, v2 times V3 is going to be V2 and V3. So it's going to be -6 times -4 plus 3 times -6 plus -3 times 2 plus 0 times 7. And the result, this is 24 minus 18 minus 6. And the result is going to be 0. So now the multiplication of V1, V2, or V3 equals 0. In this case, that means this is an orthogonal set. These three vectors, or this set, is an orthogonal set. Because the dot product between any two vectors from this set equals 0. So V1 times V2. V1 times, or not times, the dot product between V1 and V2. So it's going to be -1, 1 times -1. So 1 times -1 plus 0 times 0 plus -1 times 1 times 1 plus the last is 1 times 2. So 1 times 2. So the result is going to be -1 plus 0 minus 1 plus 2. And then it's equal 0. Because -1, -2 plus 2 is going to be 0. Now V1 times V3. The second one, V1 times V3. So it's going to be 1 times 1, 1 times 1 plus 0 times 1, 0 times 1 plus -1 times 1 plus -1 times 1. This is the third one. And the fourth one is 1 times 0. 1 times 0. So this one is going to be equal 1 plus 0 minus 1 plus 0, and the result equals 0. Now V1 times V4. So until now, it's okay. Now V1 times V4 is going to be 1 times 0 plus 0 times -1 plus -1 times 1 plus 1 times 1. So this one is 0, this one is 0. So 0 plus 0 minus 1 plus 1, and the result equals 0. Next one is going to be V2 times V3. So you have to check all the dot product between all these vectors. So V2 now times V3. So V2 is going to be -1 times 1 plus 0 times 1 plus 1 times 1, and the plus, the last one is 2 times 0. So it's going to be, this is -1, this is 0, plus 1, plus 0, and the result is going to be 0. Now V2 times V4. V2 times V4. So V2 is going to be -1 times 0 plus 0 times -1 plus 1 times 1 plus 2 times 1. So this is 0 plus 0 plus 1 plus 2, and the result is 3. If you check V, the last one, V3 times V4, let's check this one. So v3 times v4 is going to be 1 times 0 plus 1 times -1 plus 1 times 1 plus 0 times 1. This is 0 minus 1 plus 1 plus 0, and the result is 0. So we already found the dot product between all these vectors is zeros, except vector 2 times vector 4. Vector 2 times vector 4 equal 3. And this one is also 0. In this case, this is not orthogonal set. Why? Because the multiplication of vector 2 times vector 4 is not 0. So this is not orthogonal set. That means when they ask you about the orthogonal set, you have to check all the vectors. You have to check the dot product between all these vectors, and it's supposed to be equal 0. So we don't have to check this theorem because we have 3 vectors, v1, v2, and v3. They ask you the given set does not orthogonal base, or the given set is orthogonal base. Here's the theorem. Let v1, v2, and vk be an orthogonal base for the subspace W on Rn. So we have a subspace W in Rn. And let W, be careful, this W is different than the subspace. Be any vector in the subspace. Then there is unique scalars C1 and C2 such that the W, which is a vector in the subspace, is a linear combination with C1, C2 until C from these 3 vectors. The main thing here, use the theorem to express W as a linear combination of the above basis vectors, given the coordinate here, and to write down, we have the W, which is a vector in the subspace, and here we're just gonna write down the scalars C1, C2, and C3. How to find these scalars? We're gonna use this one. They're telling you C1 is, first of all, I'm gonna write down the vectors. V1 equal 2, 0, and -2. And V2 equal 3, 6, 3. And V3 equal 1, -1, and 1. We already have the W, which is equal vector 1, 1, 1. We're going to find the scalars C1. So the first thing I'm going to say C1 equal W times V1 over V1 dot product between W and V1 and V1 with the V1. So it's going to be the dot product between W and V1. W is the vector 1, 1, 1. So it's going to be 1 times 2 plus 0, 1 times 0 plus 1 times -2 over V1 times itself. Of the dot product between V1 and itself is going to be 2 times 2 plus 0 times 0 plus -2 times -2. In this case, it's going to be 2 plus 0 minus 2 over 4 plus 0 plus 4. And 2 minus 2 is going to be 0. 0 divided by any number is going to be 0. So the first scalar is 0. C2 is going to be the subspace W times, not times, the dot product with V2, and V2, the dot product with the itself is going to be W is 111, so 1 times 3 plus 1 times 6 plus 1 times 3. And everything is divided by 3 times 3 plus 6 times 6 plus 3 times 3. And it's going to be 3 plus 6 plus 3 divided by 9 plus 6 times 6, which is 36, plus 9. So on the top, this one is going to be 12, because 9 plus 3 is going to be 12. And here is 9 plus 9 is going to be 18, plus 36 is going to be 54. In this case, simplify this one is going to be 2 over 9, because this one you can divide by 6, which is 2 over 9. So here is the second scalar. The third scalar is going to be the subspace dot product with the V3, and V3 dot product with itself is going to be, here is V3, so it's going to be 1 times 1 plus 1 times -1 plus 1 times 1 over V3, which is 1 times 1 plus -1 times -1 plus 1 times 1. And then this one is going to be equal 1 minus 1 plus 1 over 1 plus 1 plus 1. So it's going to be 1 over 3. That means W sub B is going to be 0, 2 over 9, 1 over 3. Let's check these three numbers. So here is 0, and now 2 divided by 9, and the last one is 1 divided by 3. That's it for this example. So again, orthogonal set, that means the dot product of any two vectors in this set equals 0. But if the length of each vector equal 1, that means this is called orthonormal set. So let's check with this example. Example 5. Example 5, we have these two vectors. So now, before we check that, because it says the set is orthonormal if it's orthogonal and the length for each vector equal 1. First of all, we have to check if this is orthogonal. That means V1 dot product with V2 is equal 20 over 29 times 21. So 20 over 29 times -21 over 29 plus 21 over 29 times 20 over 29. The result 100% equals 0. Because the same numbers, that means the result from here is going to be negative, the result from here is going to be positive, and the result is going to be 0. Now we need to check the length of V1, which is equal the square root of 20 over 29 squared plus 21 over 29 squared is going to be equal the square root of 20 squared is 400 over 29 squared is going to be 800 something. Let me check. 841. A plus 21 squared is a 21 times a 21. So it's going to be 441 over 841. Add these together. So it's going to be 841 divided by 841. And this one is going to be square root of 1, which is 1. That means the length of V1 is equal 1. Now we need to check the length of V2 equal 1. If the length of V2 equal 1, that means this is orthonormal set, because the dot product between V1 and V2 equals 0, and the length for each vector equal 1. So the length of V2 equal the square root of, to be the same thing, negative 21 over 29 squared plus 20 over 29 squared. And it's going to be the square root of, this one is going to be 441 over 841 plus 400 over 841. And this one is going to be the square root of 841 divided by 841. And it's going to be the square root of 1, which is equal 1. That means the length of V2 equal 1. So in this case, this is the set is orthonormal. That's it for this example. So let's check the first thing, the dot product between these two vectors. V1 times V2 is going to be equal half times half, which is 1/4, plus half times negative half. So it's going to be 1/4 minus 1/4, and this one is going to be equal 0. That means, yes, it's orthogonal. These two vectors are orthogonal. So this is orthogonal set. Now we have to check the length for each vector. The length of V1 is going to be square root of half squared plus half squared. It's going to be square root of 1/4 plus 1/4. Then it's the square root of 2/4, which is the square root of 1/2. And this is 1 square root of 2. This is not equal 1. So in this case, this is not orthonormal set. By just proving the length of the first vector is not 0, that means this is not orthonormal set. So we're going to just type here 1 over the square root of 2. Now they ask you to find the length of V2. Let's find the length of V2, and it's going to be the same thing because this one is squared, so also it's going to be 1 over square root of 2. So here also is going to be 1 over square root of 2. But this set is not orthonormal. So that's it for example 6. So they're telling you determine whether the given matrix is orthogonal. This matrix is orthogonal. How are we going to check that? So there is a theorem that says the columns of an M times N matrix Q form orthonormal set. Orthonormal set, that means the columns, the dot product of these two columns equal 0, and the length for each column is equal 1 because it's orthonormal. That means the dot product. So if you have a Q equal column 1 and column 2, orthonormal, that means the dot product of the first vector with the second vector equals 0 with these two columns, and the length for this vector equal 1, and the length for the second vector, which is the second column, equal 1, because it's an orthonormal set if and only if the dot product of the multiplication now with the matrix Q transpose and the Q equal IN. So if they, with this example, they're telling you show that this matrix is orthogonal. That means if I find the transpose and multiply the transpose with this matrix, and the result is the identity matrix, so this matrix is orthonormal, and in this case, it's orthogonal. So let's work on the first part. Q transpose is equal, the first row is going to be the first column. That means going to be half and square root over 3 divided by 2. And the second row is going to be the second column. So it's going to be negative square root over 3 divided by 2. And here is going to be 1 divided by 2. So this is the Q transpose. Now, if I do the multiplication between Q and Q transpose, by this theorem, Q transpose times Q is going to be 1/2 square root over 3 over 2. And here is negative square root over 3 divided by 2. And here is 1/2 times the transpose. This is the transpose. No, this is, here is the transpose. And this one is negative times Q, which is half square root over 3 divided by 2, and negative square root over 3 divided by 2, and negative 1/2. The multiplication between these two matrices is going to be half times half, which is 1/4, negative square root of 3 times, so this one is going to be, this is the transpose, and here is the original Q. Okay, 1/2 times this one is going to be 1/4, and this one times this one, so it's going to be plus 3/4. And the first row times the second column, so it's going to be 1/2 times Q square root of 3 divided by 2. So it's going to be square root over 3 divided by 4. And this element times the second one is going to be negative square root over 3 divided by 4. Now the second row times the first column. So it's going to be square root over 3 divided by 4. And this one times this one, so minus square root over 3 divided by 4. The second row times the second column, square root over 3 times square root over 3 is going to be 3/4. Plus half times half is going to be 1/4. That means the result here, this is 1, this is 0, this is 0, and this is 1. So the multiplication between Q transpose and Q equal identity matrix. That means Q is orthonormal. And if Q is orthonormal, that means Q is orthogonal. So that's how to prove the orthogonal matrix. So we're just going to type Q is orthogonal matrix. Now we need to find the inverse. There is another theorem. The second theorem, it says a square matrix Q is orthogonal if and only if the inverse for this matrix equals the transpose. So this theorem, there's a proof for this theorem, and check it to make everything easier for us. I have a orthogonal matrix, and they asked me to find the inverse. So the inverse is going to be equal to the transpose. That means by theorem 5.5, Q inverse is equal Q transpose, and this one equal, here's the transpose. That means this is the inverse for Q. Square root of 3 divided by 2, and square root of 3 divided by 2, and 1 over 2. That means the inverse for Q is going to be this matrix. 1 over 2, and here square root of, they're telling you enter scat in for this one. So we have to write down SQRT as square root over 3. Square root over 3. And here we're going to type the same thing. The square root over 3 divided by 2. And wait a minute, how are we going to type the negative? So it's negative. And here is the same thing, but it's positive. Divide by 2. And here is 1 divided by 2. Let's check that. It's QRT, yes. That's it for this example. I used theorem 5.4 and the last theorem, which is 5.5. So example 9, you're going to do exactly the same thing. Let's go to example 10. Let's check example 10, how we're going to solve this one. Here, they're telling you the following facts can be proven. They're not going to ask you to prove that, but you can prove that an orthogonal 2 times 2 matrix must have the form. It's orthogonal. That means have this form, because why? Because when you find the dot product between this matrix and this one, the result is supposed to be 0. Where A and B is a unit vector that means the length for this vector is equal 1. The second fact is every orthogonal 2 times 2 matrix, they're talking about 2 times 2 matrix, is not 3 times 3 or 4 times 4. Every orthogonal 2 times 2 matrix is of the form this one or this one. That means the theta is going to be between 0 and 2 pi. The third one, any orthogonal 2 times 2 matrix corresponds to rotation in R2 if the determinant of Q equal 1 and reflection if the determinant equal -1. Now we're going to use these 3 facts, use above facts to determine whether the given orthogonal matrix represent a rotation or reflection. So rotation or reflection. That means we're going to find the determinant for this matrix. So example 10, we have the matrix Q equal -, square root of 3 divided by 2. And here half. And here is negative half. And here is negative square root of 3 divided by 2. So here is the matrix. We need now to check if it's rotation or reflection. We're going to find the determinant. Determinant if equal 1, that means this is rotation. Rotation. If it's equal -1, it's reflection. So the determinant for Q is going to be equal negative square root of 3 divided by 2 times negative square root of 3 divided by 2 minus half times negative half. This one is going to be equal negative times negative positive, so it's going to be 3 over 4. Negative times negative is positive, 1 over 4. And it's going to be 4 over 4, and the result is 1. That means it's rotation. That means this one is rotation. And here's the thing. If it's rotation, give the angle. We need to find the angle. If it's reflection, you have to give the line. Now let's check how we're going to find the angle. We're going to depend about this one. Check, you're going to use one of these matrices because it's 2 times 2 matrix. That means you can use this one or you can use this one. Now let's compare between cosine theta and the angle here. Sine theta and the angle here. That's what we're going to do with this example. So let's check. Cosine theta, that means cosine theta here is equal to this number. So I'm just going to say cosine theta equal negative square root of 3 divided by 2. And I'm going to say sine theta equal negative half. So if you check the coordinate for the sine and the cosine, sine positive and cosine is positive. Here, the sine is positive, the cosine is negative. Let's say here sine, and here is cosine. This is the sine is positive, and the cosine is, because we need to work on the coordinate. Both positive, here is the sine positive, here is both negative, and here is the cosine is positive. So here's the coordinates. Now our sine and the cosine is negative. That means our angle here on this coordinate. So our reference theta is going to be, let's check the reference. Is going to be theta reference is going to be, which theta is the sine for this theta equal negative half or half. The theta is 30, because if you check cosine or sine to the 30 is going to be half, which is equal to this. That means our reference theta is going to be 30. But I need to get on this coordinate. So our theta is going to be 180 plus 30. Here, you're going to say 180 plus the theta, the reference. Here, you're going to say just the theta reference, exactly the same thing is going to be. Here is going to be 180 minus theta reference. And here is going to be 36, which is 2 pi minus theta reference. So now we're going to add the reference. So our theta is going to be 180 plus 30. It's going to be 210. So this is our theta for this example. 210. Yeah, type here 210. That's it for this example. Let's see, 180, 20, 20 to 10. Oh, I'm gonna find the degree here. So 210 degree. So we have to put the degree. Be careful. You're not gonna just plug in 210. It's considered wrong. You see, that's right.